We now come to the question number 21. The question is given as a hole is bored along the diameter of the earth and a particle is dropped into it. If r is the radius of the earth and g is the acceleration due to gravity at the surface of the earth, then find the time period of oscillation of the particle. The first option is your 2 pi root over r by g. Second option 2 pi root over r by 2g. Third option 2 pi root over 2r by g. And the fourth option none of these. See, as per the given information, this is the let earth and a hole has been bored like this, and g value at the surface of earth is given, r is the radius and g is gm by r square. As we know, if we are going from center to the surface, value of g gradually increases. So, g at r distance from the center of earth is given as gm by r cube into r. So, what we have observed, suppose a particle is kept here or a particle is released. So, because the force of attraction, the particle will go in that side, and then when it crosses the origin or when it crosses the center of the earth, at this time it has certain velocity. Now, when it goes in the other side, at this side the force will act in this direction. So, it will come to rest here. So, it will oscillate from here to here like this, with the amplitude of oscillation is equal to radius of the earth. So, we can say any position, suppose here restoring force F restoring is equal to your gm by r cube into m into r at this location. The restoring force in that side, but displacement your in this side. So, the direction of this force and r is your opposite. Now, m into a is gm m by r cube into r. So, a is equal to gm by r cube to minus r. So, this is your nothing, this become your omega square, and this, as we know, on the surface of earth g is your gm by r square. So, this can be written as by g by r minus this. So, this is your omega square. So, omega square your g by r. So, time period t is 2 pi by omega, which is your under root r by g. So, this is the time period of oscillation. So, our correct option is your option number 1 is the correct option. Question number 22. It is given as a cylindrical piston of mass m and cross sectional area A slides smoothly inside a long cylinder closed at one end, enclosing a certain mass of an ideal gas at a pressure P. The cylinder is kept with its axis horizontal. If the piston is slightly disturbed from its equilibrium position, it oscillates simple harmonically. The period of oscillation is the first option 2 pi root over capital M H by Pa, second option 2 pi root over mH by pH, third option 2 pi root over m by pH, and the fourth option 2 pi root over mph. Now see this. as per the question here, this is the long cylinder and this is the piston, and this piston can move or can vibrate like this. Right now the piston is in equilibrium. It means whatever the pressure of the gas from this side, same pressure exerted by the surrounding atmosphere. So this is the equilibrium condition. So initially or at equilibrium pressure of gas is equal to atmospheric pressure. Now if the piston is slightly displaced by x, then what will happen here? The volume of this will change. The volume changes, so pressure increases, the pressure of gas will increase. Now if the piston is slightly displaced at this moment, see, initially the total volume was your V naught and pressure your P naught V naught. Now the pressure your changes, volume become your V naught minus A into x, where A is the cross sectional area of the piston and x is the displacement here. So this is the condition here. So now first condition, so restoring force on piston. So since the pressure here increases, so P A minus P naught A, this is the restoring force. So now P, value of P we can write A, P minus P naught, and the value of P is, or P minus P naught first of all, A. Now value of P written as P naught V naught by V naught minus AX minus P naught. Now further when we are simplifying, so that is equal to mass into acceleration of the piston. See, A P naught V naught minus P naught V naught minus AX by V naught minus AX. Now when further we are simplifying this, so we will get P naught V naught minus P naught V naught cancel. So here we will get P naught AX, P naught A square x by V naught minus AX, as initially as compared to V naught, AX is very small. So we can write here M A naught is approximately here P naught A square by V naught into x. This is the relation. Now further this we can simplify. See this, that can be simplified by using ideal gas equation. From ideal gas equation, PV is equal to your nRT. P is the pressure initial, P naught V naught, N is the number of moles, R is absolute temperature, R is the gas constant, T is the temperature. So now we can represent this in that form, P naught A square by V naught as per the given question. As per the given question here, initial pressure of the gas is your P and the cylinder is kept at a horizontal. So when initial pressure is P, then a value of P is given here. So V naught we can substitute the value of this here. So this term become your, now A become your P naught A square by M V naught, and this is your omega square. So now when omega square, so time period will be your 2 pi root over M V naught by P naught A, and then V naught we can get the value. So this term will be your omega square. So A is equal to your P naught A square by M B naught into X. This term will be your omega square, and now we can convert. So option number 1 is the correct answer. Question number 23. The question is this: a flat horizontal board moves vertically up and down in SHM of amplitude A. The smallest permissible value of the time period such that an object on the board may not lose contact with the board is. The first option is your 2 pi root over G by A. Second option 2 pi root over A by G. Third is pi root over A by G, and fourth is 2 pi root over A by G. As per the question here, it is given a flat horizontal board. So this is your flat horizontal board, and this board is oscillating up and down. So when this board is oscillating up and down, and it is given if any of the particle, let having mass m, is kept on the board, so the particle should not be detached from the board. So what is the maximum amplitude? So see, if we are looking the board, so when the board is going up, at that time acceleration your downward, and when the board is coming down, then the acceleration your upward. The first thing, the maximum acceleration will be at the amplitude position. So A maximum, either it is going down or it is going up, A omega square. So A maximum is your A omega square, and this will be at their amplitude position, where A is the amplitude. This, if we are looking the FVD of the particle, if we are looking the FVD of particle for board going up, since one is the weight, another your normal. So in the upward motion, acceleration of board downward, the pseudo force on the particle is your in this direction, which is your ma omega square. And if we are looking for downward, in case of downward motion of the board, mg, and pseudo force is here downward, normal your upward. So in these two situations, we can see normal force cannot be 0 when the board is going down, because n dash is your mg plus, and none of the value can be 0 here. The normal force can be 0 only when the board is moving upward. So what is the limiting condition so that the mass leave the board? For limiting condition, for which mass leave the board. leave the board. At that limiting condition, n is equal to 0. When we are looking m is equal to 0, n is 0, then what is the relation? m a omega square must be equal to mg. The m a omega square must be equal to mg. So, omega must be equal to your g by a. So, time period t is 2 pi by omega or 2 pi root over a by g. This is the time period. So, option number 4 is the correct option. Question number 24. A block of mass m is suspended from a spring and its frequency of oscillation is f. The spring is cut into two identical halves and the same block is suspended from one of the two pieces of the spring. The frequency of oscillation of the block will become. The first option your 2f, second option f by 2, third is f, 4 is root 2f. So, as per the given information, initially a block is suspended with a spring of force constant k. So, its frequency, this time period of the block as we know is given as 2 pi under root m by k. This is the time period. So, frequency f is equal to 1 by t, which is equal to here 1 by 2 pi root over k by m. So, we can say frequency is proportional to root over spring constant. Now, when the spring cut into two parts, any of the spring when cut into two parts, so always remember the product of force constant with the length of the spring, that always remain your constant. So, earlier total length is your L. Now, the length of this become your L by 2. So, spring force constant at k dash. So, k into L is equal to L by 2 into k dash. So, k dash will be your 2k. So, now the force constant become your 2k. As force constant directly proportional to spring constant. So, new. So, f by f dash is equal to your root k by root over 2k. So, f dash is root 2 into f. The new frequency will be root 2 times the initial frequency. So, our option number 4 is the correct option. Question number 25. A particle undergoes SHM with amplitude A at a certain distance x naught from the mean position. The value of kinetic energy to the potential energy equal to 5. Then, first option amplitude is equal to your 5 x naught. Second option amplitude is equal to x naught by 5. Third option amplitude is greater than x naught by 5 and less than 5 x naught. And the fourth option amplitude is your x naught by 5. Now, in case of SHM, in simple harmonic motion, kinetic energy relation is given as half m omega square a square minus x naught square, and potential energy relation is given as half m omega square x naught square. So, this is the kinetic energy and potential energy relation. As per the given question here, ratio of kinetic energy versus potential energy given here 5. Substitute the value of kinetic energy here, this term, potential energy this term here, and equate your 5. So, half m omega square cancel. So, it is left to a square minus x naught square by x naught square, which is your 5. So, a square is equal to 6 x naught square. So, x naught is equal to a by root 6. So, this is the position of your particle right now. So, we can say position of x naught or amplitude. Amplitude is your, see from here, as per the given data, our option number 3rd is the correct option. The question number 26 is the potential energy of a particle executing SHM along the x-axis is given by u is equal to u naught plus u1 sin kx. The frequency of a small oscillation equal to, the first option here, k by 2 pi root over u naught by m. Second option, k by 2 pi root over u naught minus u1 by m. Third option, k by 2 pi root over u naught plus u1 by m. And the fourth option, k by 2 pi u1 by m. So, in the question here, potential energy given as u is equal to u1 plus u1 sin kx. u naught plus u1 sin kx, this is the potential energy. As we know, force is defined as minus du by dx. The force on the particle, differentiate this one. So, minus u1k cos kx. This is the force on the particle. Now, after that, if we are looking the equilibrium position, so for equilibrium f is equal to 0. f0 means cos kx will be 0. That gives us kx is equal to your pi by 2. So, when kx is equal to pi by 2 or x is equal to your pi by 2k, at this position net force is equal to your 0. Now, we want your restoring force. So, when we are displacing the particle from this position, then we can get the restoring force. Let displacement of particle from this position is x dash. Displacement of particle from mean position is x dash. So, restoring force F restoring, that is minus u1k cos k x plus x dash. This we can expand. Now, on expanding, cos a plus b, that we can write cos kx cos a cos b and minus sin a sin b, like this. Now, as we know here, then F restoring, see cos kx value here, it is your kx is equal to your pi by 2. So, when we are putting the value of kx here pi by 2, this term will be 0, and here cos kx is pi by 2. So, our value will become here u1k 0 minus sin kx, kx pi by 2 is 1. So, minus sin kx dash. Since displacement is very small, so F restoring is your u1k square. Then acceleration A is equal to your u1k square by m x dash. So this term called as omega square. So that gives us omega square is equal to u1 k square by m. So frequency f is your 2 pi root over or u1 by m, and k square we can take outside. The frequency or k by 2 pi root over un by m. So our correct option is your option number 4. Question number 27. The angular frequency of a small oscillation of the system shown is the first option root over k by 4m, second option root over 2k by m, third option root over 4k by m, and the fourth option root over k by m. Our system is given like this. In the system, one spring is given and another mass like this. Spring have force constant k and mass is your m. Now, if the mass slightly displaced, then you have to find time period of oscillation. See, at equilibrium, if we are looking here, so one is your mg, here tension T, this is also tension, this is tension T here. Let elongation in the spring your k x naught. So at equilibrium T is equal to mg and T plus T, 2T is equal to kx naught. So 2T is your kx naught. So that gives us 2 mg is equal to your kx naught. This is the condition for equilibrium. If this mass is slightly displaced, let x, from equilibrium, if it has been displaced by x equilibrium, so displacement of the spring, let here x dash. So from constraint equation first, if it come down x dash, so x dash length get free here, x dash get free here, so 2x dash must be equal to x. So 2x dash must be equal to x. This is second equation. As it has been displaced, tension will change, the restoring force, F restoring now, T dash minus mg. This T dash, 2T dash is new value of spring force, that your k x naught plus x dash. Substitute the T dash value over here. So F restoring, this is your k by 2 x naught plus x dash minus mg. So from first relation, k x naught by 2 is your mg, this and this cancel. So it left only k by 2 x dash. So acceleration is your k by 2 m into x dash. This term is your omega square, and they are asking the omega value. So omega square is your k by 2 m. So angular frequency will be a root over k by 2 m. So this is our correct option. So option number first is the correct answer. Now question number 28. The displacement of a particle varies according to relation x is equal to 4 sin 3t minus 3 cos 3t. The maximum speed of the particle is the first option 12 meter per second, the second option 15 meter per second, third option 3 meter per second, and the fourth option 21 meter per second. So as per the given, the displacement of the particle varies as x is equal to 4 sin 3t, 4 sin 3t minus 3 cos 3t. 3 cos 3t. This can be written as 4 by 5 sin 3t minus 3 by 5 cos 3t. 4 by 5 is sin 53 or cos 37, and 3 by 5, so that can be written as 5 cos 37 sin 3t minus sin 37 cos 3t. So this is nothing, 5 sin 3t minus 37 degree. This is the displacement of a particle. Now velocity. If we want velocity, v is nothing, dx by dt. Differentiate this one. 15 cos 3t minus 37 degree. So v maximum is the value when the cos term become your maximum, which is your 1. So this become your 15 meter per second. So maximum velocity or 15 meter per second. The correct option, your option number 2. The question is given as a particle undergoes two simple harmonic motion in mutually perpendicular direction given by x is equal to a sin omega t minus pi by 3 and y is equal to a sin omega t plus pi by 6. The path traced out by the particle in the xy plane is, the first is the straight line, second is the parabola, third is the ellipse, and fourth is a circle. Now see, as per the given equation, x is equal to your a sin omega t minus pi by 3, while y is equal to your a sin omega t plus pi by 6. Now, since there is a path difference between these two are 90 degree, so that can be, if we are looking the relative value here, that can be said x dash is equal to your a sin omega t, and y dash can be said a sin omega t plus pi by 6 plus pi by 3, pi by 2. So y dash written as a cos pi by cos omega t, like this. Now from first and second, let this is your first and second. From equation 1 and 2, x dash by a square, x dash by a square means sin square omega t, plus y dash by a square, which your cos square omega t, that should be your 1. The x dash square plus y dash square is equal to a square, and this is the equation of a circle. This is the equation of circle. So our correct option is the circle. So option number 4 is the correct option. Now see the question number 30. Question is given as two light spring of force constant K1 and K2, each given as 3.2 Newton per meter, and a block of mass 200 gram are in one line AB on a smooth horizontal table such that one end of the each spring is fixed on the rigid support and the other end is free as shown. The distance CD between the free ends of the spring is 60 centimeter. If the block moves along AB with a velocity 120 centimeter per second in between the spring, the period of oscillation of the block. The first option 1 second, second option 1.57, second, third option 2.57 second, and the fourth option 3.57 second. See, as per the question here, this is the wall or rigid support, and there are two spring here. One is this, another is this, both having the same force constant K. Directly we can say K is 3.2 Newton per meter, it is given. And now between these are the two C and D point, 60 centimeter the gap between these two. A particle moves with velocity 120 centimeter per second between C and D. So when particle goes here, it compresses, come back here, then go back. Then it travel here, then it compresses, then come back. Then it is reaching here. So total time means T by 2 here, T by 2 here. So total time T is equal to T plus this distance here 60 plus 60, 120 with speed 120 centimeter per second, that time is your 1. So T is 2 pi root over m by k plus 1. And mass of the particle is given 200 gram, and force constant your 3.2. The 200 means 0.2 by 3.2 plus 1. So this is your 1 by 16. 1 by 16 means 1 by 4. So this will be your pi by 2. So this will be pi by 2 plus 1. So T is your pi value your 1.57 plus 1. This is your 2.57 second. This is the time period of oscillation. So our correct option here, option number 3. Question number 31. Two masses M1 and M2 are suspended together by a massless spring of constant K. When the masses are in equilibrium, M1 is removed without disturbing the system. Then the angular frequency of oscillation of M2 is first option root over K by M1, second option root over K by M2, third option root over K by M1 plus M2, and the fourth option root over K by M1 minus M2. See, initially two masses was attached, M1 and M2. So only the difference is that spring force Kx naught in equilibrium M1 plus M2 into G. So x naught is the elongation. Now they are saying mass M1 is removed. If we are removing the mass M1, let this is the value of your x naught. This is the value of x naught. When M1 has been removed, only M2 left, and spring have remained same force constant K. So neither force constant changes, only mass M2 is there. So whatever the frequency, that is because of the spring constant K and M2. So angular frequency omega will be here K by M2 root over. No difference, no effect of the removal of mass M1. Only things can be done that from that we can get the amplitude. Amplitude may be different. If we are looking the amplitude, then the case will be different. This is the initial elongation. But if I am talking about the amplitude, after removing M1, what is the mean position? After removing M1, the new mean position will be, the new mean position will be x naught dash, which is equal to your m2g by k. So amplitude of oscillation. So amplitude of oscillation A is equal to x naught minus x naught dash. The x naught is your m1 plus m2 into g by k, and x naught dash is your m2g by k. So amplitude will be only that will affect m1g by k, but the angular frequency will remain same. Omega is your under root k by m2. So our correct option, your option number 2 is the correct option.